we will focus on using Venn diagrams in basic probability theory. In Lesson 1, the focus will be on basic concepts, terminology, and notation. Outcomes for Lesson 1. In this lesson, we will focus on explaining the meaning of concepts and terminology linked to probability statistics. We will focus further on examples of random experiments. The focus will also be on the definition of theoretical probability and finding the theoretical probability of events. Let us consider a few introductory remarks. Probability is the mathematics of chance. Some examples. Firstly, the probability that it will rain in Port Elizabeth today is 0,3 or 30%. Second example, the probability of contracting the flu virus is 70 to 100, which is the same as 70%. And thirdly, the probability of winning the lotto is about 1 over nearly 14 million, or as a percentage, 0,507%. Probability can thus be reported as a fraction, a decimal, a percentage, or a ratio. The greater the probability, the more likely the event is to occur. Conversely, the smaller the probability, the less likely the event is to occur. If we look at the three examples, there is a strong probability that you may contract the virus because the probability is 70%. There is a reasonable chance of rain in PE today because it is 30%. But there is almost no chance of you winning the lotto, because if we round this off to the nearest fourth decimal, then you see the chances are actually 0%. Let us look at certain terminology related to probability. A random experiment is an experiment in which certain physical actions are repeated many times to establish the frequency or the number of times that a particular event will occur. For example, a coin may be flipped 1,000 times in a particular random experiment. So the physical action here is the flipping of the coin, after which it will be possible to establish how many times heads and how many times tails have realized. So how many times the heads comes up is the frequency for heads, how many times tails come up is the frequency for tails, while the two events in this case will be heads or tails. In each time that an experiment is carried out is known as a trial. So in this previous example, there will be 1,000 trials. An outcome is one of the possible things that can occur as a result of an experiment. For example, H in this experimental example of tossing a coin, H, which we can use to indicate heads, and T, which we can use to indicate tails, are the two possible outcomes in this coin flipping experiment. The set of all possible outcomes is called a sample space. So in the coin tossing experiment, the sample space S is the set containing the two outcomes H and T. So this is the sample space, while the subsets, the set H and the set T, are two possible events. We are now going to look at a few experiments. So tossing a single coin in an experiment is the first experiment that we will look at. So here we toss a coin and record after each trial whether the side up is heads or tails. So we can either get heads or tails. So there will be two possible outcomes, namely H or T, which we will use to indicate heads or tails. Hence the sample space, which is a set, is the set S containing the two outcomes H and T. And the number of elements, or the cardinal number of the sample space, is 2. Now if you know the cardinal number of the sample space, you can work out the number of events. So there will be 2 to the power 2, or 4 events in this experiment, since an event is simply the subset of a sample space, and the events in this experiment are therefore the empty set, the set containing the element H, the set containing the element T, and the set containing both the elements. These 4 events can be described in a verbal way. For instance, if we look at the event where we have the subset H, this description can be linked to getting heads, while the event, namely the subset T, is getting tails. Well, if we look at the event where we have both, namely the sample space itself, remember a set is always a subset of itself, this can mean getting either heads or tails. And then we can have the empty set. In other words, an event where there is no outcomes in. Now it's possible to toss a coin and it may roll and end up against the wall, lying on its side. Therefore you can get neither heads nor tails. Just one remark. It is not always possible to give descriptions of the different events. In this relatively simple experiment, it is possible to give a clear description of each of the 4 events. Roll a 6-sided die in an experiment is what we focus on now. So in experiment 2, we will roll a 6-sided die and record the number of dots showing on the top face after each trial. So here is a 6-sided die with either 1, 2, 3, 4, 5 or 6 dots on the top face. So for this experiment, the sample space S is the set containing the 6 outcomes. And there will be 2 to the power 6, where 6 is the cardinal number of this sample space. So there will be 2 to the power 6, or 64 possible events. Pascal's triangle can assist you to determine the 64 events. If you should add the numbers in this bottom row where the second one is 6, you will get 64 events. I hope you understand the construction of Pascal's triangle. Just to backtrack a little bit, in the coin tossing experiment, there we've seen that we had 4 events. That one means getting the empty set. This one meant getting the head as one event, or the set T. And the last one was getting either heads or tails. Some examples. We can see in this there are 15 events containing two numbers. So if I focus on this particular one, and this we can translate to a verbal description, getting either the one or the other number. So one of two numbers. For instance, that one will mean getting none of the 6 numbers. It is possible to roll a die so that it can end on its corner, right, against some object. Or you can roll it and you can get either a 1, a 2, a 3, a 4, a 5, or a 6. That's that 6. Here we're talking about getting one of two numbers. So I could easily list this 15 events. You can either get a 1 or a 2, a 1 or a 3, a 1 or a 4, 1 or a 5, 1 or a 6, so that's 5 already, a 2 or a 3, a 2 or a 4, a 2 or a 5, a 2 or a 6. You just have to work systematically to account for all the possible events. You can get a 3 or a 4, 3 or a 5, 3 or a 6, 4 or a 5, 4 or a 6 or a 5 or a 6. So this is the 15 events. So you can also go about to list all the other ones. That 20 will simply mean there will be 20 events where you can get any of 3 possible numbers. So you can get either a 1, 2, or a 3, a 1, 2, or a 4, and so on. If you go through that procedure, you will get 20. So the listing and the describing of the remaining 49 events are left as an exercise. Let us consider the role of a pair of dice in an experiment. So in experiment 3, we roll a pair of 6-sided dice and record either the number or the number of dots showing on the top face of each die after each trial. Now we get 2 different types of die. Here you see a number die, and there you also see the internet reference where I obtained this particular image. So this is a number die, while this one here is, we can call it a dot die. So getting a 3 on this one will mean you get the number 3, while getting a 3 here will mean you get 3 dots. So this is just so that we can make a clear distinction between the 2 different outcomes. So what we record here is we record the pair of outcomes. So in this particular experiment, for each trial, we record the pair of outcomes. So for this experiment, the sample space consists of 36 ordered pairs. You see there's 6 outcomes there and 6 outcomes there, so 6 times 6, that's 36. More about this in grade 11. So the number of outcomes will be 36, while the number of events will be 2 to the power 36, quite a few. The 36 ordered pairs can be illustrated graphically. So each outcome here is an ordered pair. So 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, where the first number is the outcome for die 1. Now let's call die 1 the number die. And the second number in the ordered pair is the outcome for die 2, which is the dot die. So clearly you will get 36 outcomes. Please just take note, the 2 that I've marked in red here, the outcome 5, 3 and the outcome 3, 5 are different outcomes, because 5-3 can mean that you get 5 dots and the number 3, while 3-5 can mean that you get 3 dots and the number 5. So there are many such pairs where the two are interchanged. I mention this because I know a lot of people find it very difficult to understand why 5-3 is different to 3-5. Remember, it is ordered pairs where the first display indicates the display of the white die, while the second one indicates the display in this ordered pair of the red die. Next, we consider drawing a card from a standard pack of cards in an experiment. So in experiment 4, a card is drawn from a standard deck of playing cards. Those of you that don't know playing cards, we have 13 clubs, 13 spades, 13 hearts, and 13 diamonds. So for this experiment, the sample space consists of 52 outcomes because there's 52 different cards. And there will be 2 to the power 52 events. Quite a large number. I leave this for you as a challenge and an exercise to read this. Give a name to this. Don't read 4503, 599. Find a proper name for this number. Now if we look at the events, we say there's 2 to the power 52 events. It's impossible, really. Not impossible, but it will take a very long time to list and describe all these events. Just to show you one example, for instance, the event of drawing a face card. In other words, getting one of these 12 cards. Then this event can be illustrated in this way. So in other words, you either get a jack, a queen, or a king. So this will be 12 cards out of the 52. This is just one of the specific events. Let us look at theoretical probability. Now probability is a real number in the closed interval 0, 1 that describes how likely it is that an event will occur. A probability of 0 means that an event will never occur. So in other words, it's impossible. A probability of 1 means that an event will always occur. So in other words, it's absolutely certain. While a probability of 0.5 or 50% means that an event will occur half the time, or there is a 50-50 chance that it may occur. We define the theoretical probability of an event as the probability of an event is the number of outcomes in an event, which is the cardinal number of the event, divided by the number of outcomes in the sample size, which is the cardinal number of the sample size. Now the probability of the event, which is the empty set, is 0. Think in terms of our examples that we had. If you can give an example where the probability is 0, while the probability for the sample size, not sample size, sample space, right, is 1, and the probability of an event will be smaller or equal to the probability of the sample space, but greater or equal to the probability of the empty set event. So therefore, in terms of numbers, the probability of an event is always smaller or equal to 1, but greater or equal to 0. Let us look at theoretical probability from a single coin tossing experiment. Now, when we toss a coin, we have mentioned earlier that we get 4 possible events, and we've given a clear verbal description for each event. Now, if we look at the probability, the theoretical probability for each of these events, then we see that the probability of getting heads, which is the probability of event 1, is the cardinal number of event 1. There's only one outcome, namely H in this event, divided by the cardinal number of the sample space, which in this case is 2. So there's 2 outcomes. So therefore this probability is a half or 50%. So here we have a 50-50 probability. In a similar way, the probability of getting tails is the probability of event 2. So it's the cardinal number of event 2, which is 1, divided by the cardinal number of event S, which is 2, and that's also a 50% probability of 0.5. While the probability of getting either heads or tails is the probability of E3 or the probability of S. So you can either say it's a cardinal number of E3 over the cardinal number of S, or the cardinal number of S over the cardinal number of S, which is 2 over 2, or clearly 1. So it is absolutely certain that you will either get a head or a tail. And then the probability of the event in which there is no outcome, so that means the probability of getting neither heads nor tails. Remember, we've described this earlier, it is possible that this can happen. So in other words, such a trial really consider, or we will say that it's a failure. If you play a cricket match and you toss a coin and it will land on its edge, then they will have to re-toss that particular coin. But in this case, the cardinal number of event 4 is 0, because there's no outcome in this particular set, divided by the cardinal number of S is 2, and therefore the probability is 0 or 0%, so it is impossible that this will happen. Let us consider the theoretical probability that we can obtain from rolling a single die in an experiment. Here are the 6 possible outcomes in such an experiment. So the sample space consists out of the set containing the 6 outcomes, and therefore the cardinal number of S is 6. We can now identify various experiments. So the first one, what is the probability of getting a number smaller than 3? So therefore the event is the set containing the numbers 1 or 2. So the probability of such an event is the cardinal number of the event, which is clearly 2, divided by the cardinal number of S, which is 6. So the probability is 1/3, or 33.33%. The probability of getting an even number, now in the event getting an even number, in this case we have a set containing the outcomes 2, 4 and 6, so therefore the cardinal number of the event is 3. So the probability of this particular event is the cardinal number of the event, which is 3, divided by the cardinal number of the sample space, S, which is 6. So the probability is a half, or 50%. So here we have a 50-50 chance of this event taking place or occurring. In the third example, what is the probability of getting a 6? So the event here is the subset containing the element or the outcome 6 only. So the probability of the event being the cardinal number of the event, which is 1 divided by the cardinal number of S, is 6. So the probability is 1 over 6. And finally, the probability of getting a number greater than 6. Now, if we write down this subset, we're going to find that it's the empty set, because there's no number greater than 6 here. So the probability of this particular event is then the cardinal number of this event, which is 0, divided by the cardinal number of S, which is 6. So that is 0. So therefore it is impossible that this particular event will occur. Next, we look at the theoretical probability from drawing a card experiment. Now, here is an illustration of the 52 cards in a standard deck. So therefore the cardinal number of S, the sample space, is clearly 52. So we can identify various events. For instance, the event drawing a diamond. So what is the probability of drawing a diamond? Now the event is the set containing the 13 cards in this bottom row. So the cardinal number of the event is clearly 13, divided by the cardinal number of S, which is 52. So therefore the probability is a quarter, or 0.25, or 25%. The probability of drawing a diamond face card. Now, the diamond face cards are the Jack, Queen, and King of diamonds. So there is 3 outcomes in this particular event: Jack of diamonds, Queen of diamonds, or King of diamonds, while the cardinal number of S is still 52. And this, of course, you can simplify to a percentage or a decimal. The third example, the probability of drawing either an ace or a king. So there is 4 outcomes where you have an ace, and 4 outcomes where you have a king. So the cardinal number for this event is therefore 8, right? The 4 aces and the 4 kings, while the cardinal number of the sample space is still 52. So that probability is 2 over 13, which can be expressed as a percentage or a decimal or even a ratio. In the last example, the probability of drawing a face card. So the event is drawing a face card. Now, the event here can be illustrated by this 12 face cards. So the cardinal number for this event is 12. So because there's 4 jacks, 4 queens, and 4 kings, or 12 outcomes in this particular event, while the cardinal number of S is still 52, so this probability is 3 over 13. You should now be in a position to tackle tutorial 1, dealing with theoretical probabilities. So consider the experiment in which we roll a pair of 6-sided dice and record either the number or the number of dots showing on the top face. Now we have listed earlier the 36 possible outcomes as ordered pairs, and we've done it graphically. The question now is to determine the theoretical probability for each of the following events. Remember, there will be 2 to the power 36 events. We are just looking at 3 of these events. The event A is the event such that the sum of the dice is equal to 7. Event number B is described as the event such that the sum of the dice is greater than 5, while event C is the event where we can give a description that at least one die must show a 4 face up. I suggest that you pause the video, do tutorial 1, and then come back and view possible solutions. Let us consider a suggested solution to problem 1 from tutorial 1. Here you need to determine the theoretical probability of event A occurring, where event A is described that it must be such that the sum of the dice is equal to 7. Now if we look at our graphical representation, we can clearly identify the subset where the sum of the dice is equal to 7. So that will be the ordered pair 1 6, 6 1, 2 5, 5 2, 3 4, and 4 3. So clearly there will be 6 ordered pairs in this particular event. The ordered pair 1 6, 2 5, 3 4, 4 3, 5 2, and 6 1. So this is how you can write it in set notation. So that means clearly then that the cardinal number of this event A is equal to 6. Remember, the cardinal number of the sample space S we know is 36. So therefore the probability for event A is the cardinal number of event A divided by the cardinal number of S according to the definition, and this is 6 over 36 or 1 over 6. Next we look at the suggested solution to the second problem from tutorial 1. You have an event here described as the sum of the dice is greater than 5. If we look at our picture again, then you notice that the ordered pairs that I've indicated in red here are the outcomes where the sum is equal to 5. 1 4, 4 1, 2 3, and 3 2. And the blue ones below these 4 outcomes also give us sums that is less than 5, while the dots that I've indicated in black are outcomes indicating the outcomes for event B. So how many outcomes are there in event B? In other words, what is the cardinal number of event B? It is much easier to count actually the outcomes where the sum is smaller or equal to 5, and that gives me 4 plus 3 plus 2 plus 1. So 4 plus 3 is 7 plus another 3 is 10. So therefore there will be 26 outcomes in event B, and therefore the probability of event B occurring is the cardinal number of B divided by the cardinal number of S. That is 26 over 36 or 13 over 18. Finally, we look at a suggested solution to problem 3 of the first tutorial. Here you need to find the probability, the theoretical probability, excuse me, for event C, where event C is described as we must get at least one die that show a 4 face up. If we go back to our illustration, then I have shaded the event in this particular case. It really means that either a 4 must be displayed on the first die or a 4 must be displayed on the second one. Note this particular one is a common outcome. So if you count the number of outcomes here, 1, 2, 3, 4, 5, 6, 7, 8, there we find that the cardinal number for this event is 11. And therefore the probability of event C occurring is the cardinal number of C divided by the cardinal number of S, and that is 11 over 36. In lesson 2, we focus on probability and relative frequency of events. Let us look at the outcomes for lesson 2. In this lesson, we will focus on relative frequency of events. We will compare the relative frequency of events with theoretical probability. We will focus on relative frequency tables and relative frequency graphs, and we will finally look at simulation of experiments using tables of random digits. Let us look at the meaning of relative frequency of an event. Now, the relative frequency of an event is defined as the number of times that the event occurs during experimental trials divided by the total number of trials conducted. So therefore the relative frequency of an event expressed as a formula is equal to the number of times an event occurs divided by the number of trials conducted during the random experiment. Now, relative frequency is an experimental quantity and not a theoretical quantity. Due to the experimental nature, it is possible to get a different value every time that we repeat the experiment. As a formula, we can express it in this particular form, where F is the relative frequency, P is the number of positive trials, so in other words the number of times that an event occurs, and T stands for the total number of trials. So this is the formula that we can utilize to calculate the relative frequency. We now look at an example where we compare theoretical probability with relative frequency. Between you and your partner, you roll the dot and the number dice 344 times. So one of you will roll the dot die and the other one the number die. But in total it's been rolled 344 times. The following table indicates a summary of the experimental trials. So here are the outcomes with the number die. You can either get a 1, a 2, a 3, 4, 5 or 6. And this was the frequency, the number of positive outcomes during this particular experiment. And note, if we accumulate these frequencies for the number die, then you'll find that you, for instance, have conducted the experiment 163 times using the number die, while your friend conducted the experiment with the dot die, either getting a 1 dot, 2 dot, 3 dot, up to a 6 dot outcome 181 times. And there are the positive outcomes for each of the 6 outcomes. Now what can we learn from this? The theoretical probability of getting a 6 either with the dot die or the number die is 1 over 6, and that is approximately 16.7%. While the relative frequency of getting a 6 with the number die is clearly 25 over 163. So that's the number of positive outcomes of getting the number 6 divided by the number of times the experiment was repeated, say by yourself. And that gives us 15.3%. So therefore it is close but little bit less than the theoretical probability. While your friend who's rolling the dot die obtained 32 positive outcomes and repeated the experiment 181 times, so 181 trials. And this gives us a relative frequency of 17.7%, which is slightly bigger again in this case than the theoretical probability. So what do we find? What comments can we make? When a large number of trials are conducted in a random experiment, this is a reasonably large number of trials, the relative frequency of an event most of the time differ from the theoretical probability of the event. In both cases it's different. In one case it's slightly less, in the other case it's slightly more. However, the two values, namely the value of theoretical probability and relative frequency, become close to each other if the number of trials tend to infinity. So in other words, if you repeat this experiment many times. Let us look at relative frequencies in a tabulated format. Consider a random experiment in which we toss a coin 20 times and observe and record the outcome for each trial. So we have a coin and we can either obtain a head or a tail. So here are the 20 trials. So T indicates the trial and it's counted here, while P is the positive outcome. So trial 1 produces a head, trial 2 a head, trial 3 a tail, 4 a tail, 5 a tail, and so forth. So what do we find? We find that there are 9 positive H counts. 1, 2, 3, 4, 5, 6, 7, 8, 9. And obviously then 11 positive T counts or tail counts. So the frequency of H occurring, a head, is therefore 9 over 20, 20 the number of trials, and that is 0.45 or 45%. While the frequency for tails is 11 over 20, and that is 55%. The theoretical probability for H is equal to the theoretical probability for tails, and it's a half or 50%. So you can see in the one case, the relative frequency is less than the theoretical probability, while in the other case, the relative frequency is greater than the theoretical probability. Now, if we go a little bit further and calculate the frequency for a particular event being positive after each trial, we obtain this table. So let me just try and explain. After the first trial, we get a head, so the frequency is 1 out of 1. So in other words, 100%. After the second trial, we had 2 heads out of 2, so the frequency is still 100%. After the third trial, right, now we get a tail for the first time. So 1 out of the 3 is a tail, or that's 33 and a third %. Then we get another tail, so we have now 2 out of 4 or 50% as the frequency of tail. And I'll continue with this. You should be able to complete this particular table. Maybe just point out that the frequency of H, there's 9 positive trials, and there is the last one. That is after we've completed 18 trials. So at that stage the frequency is 50%, which is the same as the probability. And after we completed 20 trials, we have 11 positive T counts, 11 out of 20, so the frequency is 55%. So from the last entry, this particular one, we observe that the frequency of getting a positive outcome as tail is 0.55 or 55%. Therefore, the relative frequency of an event is approximately equal to the theoretical probability of 0.5 or 50%, as long as t tends to infinity. In other words, as long as we repeat the experiment many times. Let us look at the previous example of relative frequencies, but now in a graphical format. So we look at the graph which indicates the fluctuation in relative frequencies as the number of trials increase for each of the two outcomes. This is the table we had before. I've just separated the different trials. There are 9 trials where we had a positive head, and I've indicated the frequency in each case as the experiment continues. And here is the 11 positive ones and the fluctuation in the frequency. Now this tells us there's a fluctuation, but it doesn't show us a very clear picture. So if I plot number of trials against relative frequency, like I've done here, so you have the 20 trials here and the relative frequency, and plotting simply trial against frequency at any stage, then we get this particular graph. Note this red dotted line is the theoretical probability of 50%. So can you see the fluctuation? But eventually what happens after the experiment has been repeated a couple of times, then this particular relative frequency tends to get closer and closer to this red dotted line, which is the theoretical probability. So what can we then say? The frequency of an event tends to the theoretical probability of 0.5 or a half or 50% as the number of trials tend to infinity or tends to a very large number. Next we focus on trial simulation by means of tables of random digits. Now physical experiments such as flipping a coin or rolling a die can sometimes be time-consuming, even when all the necessary devices are available in the classroom. An efficient alternative method is to simulate such experiments by using available tables of random digits. Here is an example of such a table of random numbers. Tables like these are freely available on the internet or can easily be generated by making use of the random function available with most computer programs and even calculators. If we consider the experiment where we are flipping a coin, we can treat even digits as heads and odd digits as tails. Now in this particular table we have 4 columns of randomly generated numbers, and in each of the columns there are 32 numbers. So we have 32 randomly generated numbers. Now if we treat the even digits as head, then you'll find in column 1 there is 1, 2, 3, 4 digits ending on an even number. So we allocate 4 of the trials or the positive outcomes to heads, and obviously then 4 to tails. Well, if we look in the second column, it's only the digit ending on a 6 and an 8 that are actually even, so therefore there must be 6 odd ones. So the even ones again is allocated as a trial that is positive for heads, and the odd ones as trials that's positive for tails. So you can go on checking the third column. You should find that there are 7 of the 8 digits that's actually even. Just remember, if a number ends on a 0, it is classified as even. So obviously 1 odd. And checking the last column, you'll find that there will be 5 even and 3 odd. If we get the total of number of heads, then we find this is 18, while the total number of tails is 14. So therefore the relative frequency of getting a head will be 18 over 32, while the relative frequency for obtaining a tail will be 14 over 32. We're now in a position to do tutorial 2, dealing with relative frequencies. A bag contains different quantities of colored marbles of the same shape and size, and is indicated in the table below. So there's 9 red marbles in the bag, 7 blue ones, 6 green, 10 yellow, and 14 white. Now in a random experiment, a marble is drawn from the bag, the color recorded, and then the marble placed back in the bag. Here we have our previous table of random numbers, in which we have 32 numbers. There's 4 columns and 8 numbers in each of the columns. So we're going to use this particular table to simulate 32 trials for this experiment. By allocating a number ending on 0 and 1, we allocate to that number the color red. While blue, it will be recorded as blue if the numbers ends on a 2 or a 3. Green if it ends on 4 and 5. Yellow if it ends on 6 and 7. And white if it ends on 8 and 9. In this tutorial, it's expected of you to complete the relative frequency table for this experiment, and secondly, compare the theoretical probabilities with relative frequencies of the event. I suggest that you pause the video, do tutorial 2, and then come back and view possible solutions. Let us consider a suggested solution to the first problem from tutorial 2. So we want to complete the relative frequency table for this particular table. So we utilize this table of random numbers and we complete the table. Remember we said that if a number ends on 0 and 1, it will be recorded as a red. So if we look in the first column, we find that the last 2 numbers ends on 0 and 1, so there's 2 reds in column 1, while if it ends on 2 or 3, it will be recorded as blue. It's only the second one here that's fall in that category. Green, if it ends on got to be very careful. That was 0 and 1, 2 and 3, 4 and 5. So looking at that, you also find 1. The same for the next color, 1. And white if it ends on an 8 or a 9. And in this particular table, first column, there's clearly 3 numbers ending on a 9. Once you recorded the results for the first column, just make sure that the sum is equal to 8. So I do exactly the same for the second column and record it, column 3 the same and column 4 the same, and then I can get the total number of positive outcomes for each color. So this final total here in the last column must add up to 32. So we can now complete this frequency table. There is the colors of the marbles, the number of them in the bag, and this is the frequency or the number of positive outcomes in this particular experiment where we have 32 trials. Let us consider a suggested solution to the second problem of tutorial 2. You need to compare the theoretical probabilities with the relative frequencies. From the simulated experiment, we obtained the number of positive trials for each of the different colors of marbles in the bag from the random table. Now, we can calculate two things. We can calculate the theoretical probability as well as the relative frequency, or sometimes known as the experimental probability. So firstly, let's take the first part, the theoretical probability. Now in the bag there is 46 marbles in total, so the probability of the marble being drawn that the color is red is 9 out of 46, or approximately 0.196 or 19.6%. The theoretical probability that it will be blue is 7 out of 46, that it will be green 6 out of 46, that it will be yellow 10 out of 46, and finally that it will be white 14 out of 46. Well, in the experiment that we've simulated by making use of a random table, we find that the number of positive trials for the color red was 5 out of 32, and that turns out to be approximately 0.156 or 15.6%. While for blue it is 8 out of 32, or a quarter, or 0.25 or 25%. For green, 5 out of the 32, or approximately 15.6%. Yellow, 8 out of the 32, also 25%. And finally for white, 6 out of 32, or 18.8%. So as we've mentioned before, the relative frequency or the experimental probability is never equal to the theoretical probability. It is only when you repeat this experiment many times that we'll find that the value for the relative frequency will tend towards the value of the theoretical probability. In lesson number 3, which is the last lesson in this video, we focus on the use of Venn diagrams in probability. The outcomes for lesson 3. In this lesson we will focus on Venn diagrams as a way of representing events and related sample space. We will also focus on probability identities, mutual exclusive events, complementary events, as well as solving problems on probability, making use of Venn diagrams. Let us look at Venn diagrams and 3 ways to represent events and sample space. If we consider the following 3 sets of events linked to the sample space S, which is the set of outcomes when rolling a single die, or the set containing the outcomes 1, 2, 3, 4, 5, and 6. Let A be the event of getting an even number, and therefore it's the subset containing the outcomes 2, 4, and 6, while B, the event getting a multiple of 6, and that is the subset containing the outcomes 1, 2, 3, and 6. Now, if we make a sketch of the 2 events, then you will see that the 2 events have the outcomes 2 and 6 as common outcomes, while the outcome 4 belongs to the event A only, and the outcomes 1 and 3 belongs to the event B only, while the outcome 5 belongs to neither the event A nor the event B. So it's completely outside the 2. So you can get this situation where 2 events can have some outcomes in common. In the second example, where the event A is getting an even number, same as before, with the 3 outcomes, 2, 4, and 6, while B, let B be the event getting an odd prime number, so this is then the set containing the elements or the outcomes 3 and 5. Remember, 1 is not a prime number, because a prime number must have 2 different divisors, namely 1 and itself. If we make a sketch for this particular 2 events together with the sample space, then we find that the 2 events have nothing in common. So therefore the outcomes 2, 4, and 6 belongs to the event A only, the outcomes 3 and 5 belongs to the event B only, while the outcome 2 does not belong to any of the 2 events. So this is the second type of situation that we can get, where 2 events have nothing in common. Remember, the first one they had something in common, here they got absolutely nothing in common. The third possibility that we can get, if we consider the event of getting an even number again, and B be the event of getting a number greater than 1, so here the outcomes, or we will have a set containing the outcomes 2, 3, 4, 5, and 6. If we make a sketch of this, then we find that the event A, now remember, an event is a subset of the sample space, so therefore the event A is a subset of the set B, so it's completely contained within the event B. So the elements or the outcomes belonging to event A are also outcomes for event B, while the outcomes 3 and 5 belongs to the event B only, and the outcome 1 does not belong to B nor to the event A, but only to the sample space S. So here is the 3 typical situations. There is no other situation that you can have when you have 2 events. They either have some outcomes in common, no outcomes in common, or every outcomes in the one are also outcomes of the other one. So this is a proper subset. Here the 2 sets have an empty intersection, and there they have the set 2, 6. Right. in common. Let us look at example 1, where the identity, namely that the probability of the union of A and B, so in other words A or B, is equal to the probability of event A plus the probability of event B minus the probability of the event that belongs to A and B, or A intersection B, the intersection of two events. Now let's pick the following example that we had before, where S is the set containing the outcomes when rolling a single die, and the events A being getting an even number and B getting a factor of 6. We've made a sketch earlier of this particular situation, and we find that this is a situation where the two events have something in common. Now we want to show that this particular identity will hold for this example. Remember, this is really not a formal proof, but if we can show it for a few examples, it really means we cannot find a counterexample at this stage. So there is a reasonable possibility that this conjecture may be true. So in order to do it, let's look at the cardinal numbers of the different sets first. The set S, the cardinal number is 6. The set A, the event A, has got a cardinal number of 3. The event B has got a cardinal number of 4. The union of event A and B, so combining the two events, contain all the outcomes with the exception of the outcome 5. So the cardinal number of the union of the events A and B is 5. And in a similar way, the events where you look at the intersection of the two events, in other words, the event where the elements belong to the event A and the event B, that was the set 2, 6. So therefore the cardinal number of that is 2. Now what about the probabilities? Now the probability of A union B is the cardinal number of the union divided by the cardinal number of S, so that is 5 over 6. The probability of event A is the cardinal number of A divided by the cardinal number of S, so that is 3 over 6. The probability of event B is the cardinal number of event B, which is 4 over the cardinal number of S, which is 6. And finally, the probability of A intersection B is the cardinal number of the intersection of A and B, which is 2 divided by the cardinal number of S. So if we start off with the right hand side and look at the sum of these three probabilities, the probability of A is 3 over 6, plus the probability of B, which is 4 over 6, minus the probability of A intersection B, that is 2 over 6, so that's 7 minus 2, so that's 5 over 6. And that is clearly the probability of the union of A and B, or the probability of event A or event B. Just note, another way of saying the probability of the intersection is to say that we're looking at the probability of the event A and B, which of course is a new event, and here we talk about the probability of event A union with the event B, or the probability that event A or event B will occur. Let us consider a second example in which we would try to establish the validity of this particular relationship. We select the example that we had before, where we have two events A and B such that they have absolutely nothing in common. So in other words, their intersection will be the empty set. and we try and prove this. So as before, we would like to show that this particular relationship that exists between the probabilities of the union of two events, the event itself, the two events itself, and the intersection of the two events will be valid for this particular example. So we check first all the cardinal numbers. The cardinal number of S we know is 6. The cardinal number of A, being the set 2, 4, 6, is 3. For B is 2. The union, combining that, we get A and B, we get everything with the exception of 1. So the cardinal number is 5. And the intersection, being the empty set, will have a cardinal number that's equal to 0. Now we can find the probability for each of these 4 events. The probability of the union of A and B is the cardinal number of the union, which is 5, divided by the cardinal number of S, which is 6. The probability of A, clearly 3 over 6. Probability of B, 2 over 6. And finally, the probability of A, of the event A and B, is equal to 0, because the cardinal number of the intersection of A and B is 0. Checking this relationship again, starting with the right hand side, filling in the values for the probability of A and B being 3 over 6 and 2 over 6, as well as the probability of A intersection B, which we subtract from that, we end up with 5 over 6, which is clearly the probability of A union B. So therefore, here we have a second example where it will be valid. The good news is that you can search forever, but I don't think you will find a counterexample where it's not going to work. So at the end, we will look, and we won't do it in grade 10. You can find ways to prove this relationship that exists between the probabilities of an event A, the probability of event B, the probability of their union, and the probability of their intersection can be proved by more formal proofs. In tutorial 3, the focus is on this particular identity, which indicates the relationship between the probabilities of the union of two events, the two events itself, as well as the probability of the intersection of the two events. So let's consider the following example. S containing the outcomes when rolling a single die, and the two events, A getting an even number and B getting a number greater than 1. We had this particular example before. So I want you to do two things. Illustrate the events and sample space by means of an appropriate Venn diagram, and then confirm by means of calculating the probabilities of this 4 events. Just note that the union of two events is again an event, and the intersection of two events is again an event, so we have 4 events. So we want to show that the relationship between these 4 events will hold for this particular example. I suggest that you pause the video, do tutorial 3, and then come back and view possible solutions. Let us look at the suggested solutions to problems 1 and 2 from tutorial 3. Here we have the sample space and the 2 events. We had them before. And firstly, we draw the appropriate Venn diagram. It is pretty clear that the event A, which is a subset of the sample space, is a proper subset of the event B, which is also a subset of the sample space. In other words, set A is contained within set B. So we want to show that this relationship between the probabilities of the two events as well as their union and intersection will hold. So we start off in a very much the same way. We write down the cardinal numbers for the four events in this relationship as well as for the sample space. So the set A have a cardinal number of 3, the set B a cardinal number of 5. Note that the union of the two sets is actually the set B, so therefore it also got a cardinal number of 5, which is the same as the cardinal number of set B, while the intersection of these two events is the event A, and therefore the cardinal number of the intersection of the two events A and B is really identical to the cardinal number of event A, which is 3. And in this way we can determine the probabilities for each of these four events. The probability of A is clearly 3 over 6, probability of B 5 over 6, the probability of the union of the two events will be 5 over 6, and the probability of the intersection of the two events, which is the probability of A, like the previous one was the probability of B, is 3 over 6. So starting off with the left-hand side of this particular relationship, we have the probability of A 3 over 6, B 5 over 6. Subtract from that the probability of A intersection B is 3 over 6, so we get 5 over 6, which is the probability of the union of the two events A and B. And therefore the relationship again is satisfied for this specific example. Let us focus on mutually exclusive events, or events for which their intersection is equal to the empty set. Now here we have a definition, and we have some description of the mutually exclusive events. So I want to look at this simultaneously while looking at a specific example. Now the specific example of two mutually exclusive events is this example where the sample space is the outcomes when rolling a single die, and the events being getting an even number and an odd prime number. We had the sketch before of the two events as well together with the sample space, and what do we find? Firstly, the two events we say are mutually exclusive if they cannot occur at the same time. If you roll a single die, there is absolutely no chance that that outcome will be an even number and an odd prime number. So that is what is meant by two events being mutually exclusive. The two cannot happen at the same or occur at the same time. Alternatively, two event sets, because remember an event is nothing but a subset of the sample space, are mutually exclusive if they cannot have any elements in common, like in these two events, which implies in turn that their intersection or the intersection between the two events must be the empty set for them to be mutually exclusive, or the probability that event A and B can occur at the same time is obviously 0, simply because remember the probability of A and B is the cardinal number of A and B divided by the cardinal number of the sample space. But because A and B, A intersection B is the empty set, the cardinal number of A intersection B will be 0. So whether two events have an empty intersection or whether the cardinal number of the intersection is 0, both these implies that we have mutually exclusive events. In addition, when we have two mutually exclusive events, this relationship will be applicable. Alright, the cardinal number of A union B is equal to the cardinal number of A plus the cardinal number of B. Let's check it. The cardinal number of the union, that is 5, right? 3 plus 2, and that's the same as the cardinal number of A plus the cardinal number of B. In addition, when we have such a situation, we find that the probability of A plus the probability of B is equal to the probability of the union. For this specific example, the probability of A and B, to get that, if we go back to this formula, if we should divide throughout by the cardinal number of S, what are we going to get? The cardinal number of A union B divided by the cardinal number of S is the probability of A union B, while the cardinal number of A divided by the cardinal number of S is the probability of A, while the cardinal number of B divided by the cardinal number of S is the probability of B. So this will also be applicable in the case where we have mutually exclusive events. Just to summarize the main things, events are mutually exclusive if the intersection between the two events is the empty set, which means the cardinal number of the two, of the one and the other event is equal to 0. Furthermore, the cardinal number of the union must be equal to the sum of the cardinal numbers of the two events, and lastly, the sum of the probabilities of the two events will always be equal to the probability of their union. In this slide, we discuss complementary events, or events where the intersection between two events is the empty set, while the union of the two events is the sample space. So here we have all this detail. I'll come back to this now. But let's take such an example where we have two complementary events. Let S be the sample space of rolling a single die, and A and B the events of getting an even number or an odd number. Now, if we make a Venn diagram sketch of this, then the event A of getting an even number is the event containing the outcomes 2, 4, 6, while the event B of getting an odd number is the event containing the outcomes 1, 3, and 5. Note that the union of events A and B gives me the sample space. There is no outcomes outside the union of the two. Furthermore, the two events have nothing in common, so therefore the intersection will be the empty set. So what can we then say? Two events A and B are complementary events if and only if. So in other words, we're looking at a double implication. If firstly the intersection is the empty set, as you can see here, and their union turns out to be the sample space. In addition, the complement of A. Now the complement of A is all the outcomes not belonging to A. Right? So in other words, all the outcomes outside A. We either can use this accent or put a little bar on top of the event A. Now everything outside A but still inside the sample space in this case is B. So really we can also write it as S minus A, or the sample space, take away the outcomes that belongs to the event A. In the same way, the complement of B, which we can write as B accent or a little bar on top of the B, is really A. So every B complement is everything outside the event B but inside the sample space S. So that is clearly A, or in other words, it is S minus B. We call A and B a partitioning of the sample space. So complementary events are really when the two events are actually a partitioning, right, of the sample space. So in this particular example, if we can just check, firstly, we see that the two events have an empty intersection and that the union is equal to the sample space. Right, so therefore they must be complementary. And we can also check the additional information. The complement of A is definitely B or S minus A, and the complement of B is A or S minus B. Let us look at Venn diagrams and Venn diagrams as powerful problem-solving tools. Now, Venn diagrams can be used to solve non-routine problems, model clear verbal descriptions, and solve probability problems. Let us consider a problem which we can solve by means of an appropriate Venn diagram. Here is an example. 30 grade 10 learners were asked whether they appreciate discipline or excellent educators. The survey revealed the following. 17 learners appreciate discipline. 15 appreciate excellent educators, while 5 said they appreciate both. The question is, how many appreciate neither? Now, this particular reasonably complicated problem can easily be solved by means of an appropriate Venn diagram. Let us look at the details in this problem in symbolic format. We were given that the problem is about 30 grade 10 learners, and they were asked whether they appreciate discipline or excellent educators, and the survey revealed the following. 17 appreciate discipline, 15 appreciate excellent educators, while 5 said they appreciate both, and we had to determine how many appreciate neither. In symbolic format, we know that the cardinal number of the sample space is 30 because they interviewed 30 grade 10 learners. The cardinal number of D, let's call the event appreciate discipline. Right, all the learners that's contained in this event, we know at least it's 17. So you see, we know the cardinal numbers of the events. 15 of them appreciate excellent educators, so let's indicate excellent educators by E. And then 5 said they appreciate both, so the cardinal number of D intersection E is 5. The question was, how many appreciate neither? In other words, how many learners can be found outside the union of the two? Or you could say it outside D and outside E. In other words, not D and not E. So here is the two ways that we can express our problem, and our question is to find the value of this particular cardinal number. Let us look at the details in Venn diagrams and suggested solutions. Now this is in symbolic form, the information that was given and the problem that we are facing with. Remember, this can also be written as the cardinal number of the complement of D union E. So we construct an appropriate Venn diagram, and since we know that the cardinal number of D intersection E is 5, we can fill in this space the number of elements. Note we don't have the specific outcomes, we just indicate the cardinal number. In other words, how many learners, it can be John, Peter, Mary, whatever the names be, can be placed in this particular area. So we place the 5 in the intersection of the two events. Now furthermore, we know that the cardinal number of D, so the total number of learners present or saying that they appreciate discipline, was equal to 17. So therefore the cardinal number of D intersection E complement. Now what do we mean by this? It is inside D but outside E. Remember E complement? E complement is really everything outside E but inside the sample space. So that means that the number of learners that belongs to D but not to E, in other words this blue shaded area, or the number of learners belonging to D only, is equal to 12. In a similar way, since we know that the cardinal number of E, those appreciate excellent educators, is 15, we know that the cardinal number of those belonging to E only, in other words, E but not D, must be equal to 10. Our main problem is to find the value of X. So we can assume that the number of learners not appreciating any of these, in other words outside the union of D and E, let's call that X. What we know is that the sum of all these cardinal numbers must be equal to 30. If we set up an equation and solve it, we find that X is equal to 3, and so finally we can complete this particular diagram. Now what do we learn from this diagram? Firstly, you see if you add all these cardinal numbers you get 30. So in other words, there's 30 outcomes in this particular sample space. 5 learners appreciate both. 12 learners appreciate discipline only. 10 learners appreciate excellent educators only, while 3 learners appreciate none of the two events. So in other words, neither discipline nor excellent educators. Let us look at probability questions related to this survey. Here the results from the survey is summarized in this Venn diagram, and we know that the cardinal number of the sample space is 30. So if we look at the cardinal number of the union, in other words the shaded areas here, we find that the cardinal number of the union is 12 plus 5 plus 10, or 27. Now the union contains the students which appreciate either discipline or excellent educators. So 27 out of the 30 students, 27 out of the 30 students appreciate either discipline or excellent educators. So the probability that a selected student would either appreciate discipline or excellent educators is 90%. Well, that will imply that 10% of them will appreciate neither. If we look at the next question here, we look at the cardinal number of the event D intersection E complement. That means inside D but outside E. Inside D but outside E is that particular area that belongs to D only. In other words, the 12. And here we're talking about students appreciating only discipline. So the probability again of finding how many students appreciate discipline only is the cardinal number divided of that area, which is 12, divided by the cardinal number of the sample space. So it's 12 over 30. If you simplify this, you get 4 over 10 or 40%. So 40% of the students appreciate discipline only. If we look at the next question, which I referred to earlier, this is the students appreciating neither discipline nor excellent educators. In other words, because we can write this as well as D union, the complement of D union E, we're referring to the 3 students here. So 3 students appreciate neither discipline nor excellent educators, or the probability that a student will appreciate neither discipline or excellent educators is therefore 3 over 30, or 0.1, or 10%. The cardinal number of the complement of D, in other words, the students outside the discipline area, the students that do not appreciate discipline, is that 10 plus that 3. So 13 out of the 30 students do not appreciate discipline, and that is 43.3%. We can also calculate, I've left out a couple of other areas, like for instance this area where we find the 10 students. That's the number of students that appreciate excellent educators only. So the probability that a student will appreciate excellent educators only will be a 10 over 30, or a third, or 33 and a third percent. While the number of students outside those appreciating not excellent educators, the number of students not appreciating excellent educators, which we can write as N E complement, will be 3 plus 12. So in other words, 15 of the students do not appreciate excellent educators. So the probability that a selected student will not appreciate excellent educators is 15 out of 30, or really very high, namely 50%. I feel sorry for such a school, or containing such learners. We're now in a position to tackle the 4th tutorial, tutorial 4, in which we use Venn diagrams to solve probability problems. A survey was conducted at a school to establish how many of the 755 learners buy chips, which we will indicate by C, and how many buy water, which we will indicate by a W, during break. The following was found. 56 learners bought nothing. So the cardinal number of the number of learners outside the union of these two is 56. 486 learners bought chips. So the cardinal number of C is 486. And 517 learners bought water, so that the cardinal number of W is 517. Note the cardinal number of the sample space, which in this case is the number of learners in the school, is 755. The question is to represent this information with a Venn diagram, and then If a learner is chosen randomly, calculate the probability that this learner buys only water, only chips, water and chips, neither water nor chips, water or chips. I suggest that you pause the video, do tutorial 4, and then come back and view possible solutions. Let us look at a suggested solution to problem 1 of tutorial 4. You were given this information from a survey and you had to represent this information by means of a Venn diagram. So we assume that the number of learners that will buy chips and water is equal to X. So in this particular area belonging to chips and water, that is X, we were given that 56 learners bought nothing, so you could place the 56 outside here, while 486 of the learners bought chips. So those that bought chips only is the 486 minus the X, so this blue area. While we also were given that 517 learners bought water, so those buying water only is 517 minus X. We know that the cardinal number of S is 755. Our problem is to find X, but we know that the sum of all these cardinal numbers must be 755. So if you add up all these cardinal numbers, and in this way we get therefore an equation in X, and we can solve X, and we find that X is 304. So therefore 304 learners buys chips and water, and we can complete this Venn diagram where we indicate accurate figures. So what do we know here? 182 learners buy chips only, 304 buys chips and water, 213 will buy during break water only, and 56 will buy neither water nor chips. So this then answers the first part of the question. Let us look at a suggested solution to problem 2 from tutorial 4. Here we have all the details and the relevant cardinal numbers. The question is, if a learner is chosen randomly, calculate the probability that this learner buys only water, only chips, water and chips, neither water nor chips, or water or chips. Now, to answer the first part, only water is that part that belongs to the water only. So it is water but not chips. So the cardinal number of that area is 213. So the probability, of course, is the cardinal number of that particular event divided by the cardinal number of the sample space, which is 755. So the probability that such a learner will buy water only is 213 over 755. The probability that he will only buy chips but not water. This is what this means. Chips but not water. So it's inside the chips diagram but outside the water one. And in that particular area we find there's 182 learners. So the probability that the learner will buy chips only is the cardinal number, which is 182, divided by the cardinal number of the sample space. So therefore that probability of a learner buying only chips is 182 over 755. Of course you can express that as an approximate percentage. The third one, that the learner will buy water and chips, that is, here we focus on the intersection of the two. where the cardinal number is 304, and that probability that he will buy water and chips is clearly 304 over 755. 2.4, that he buys neither water nor chips. In other words, none of the two. And that is 56. Note the two ways. You can say it's the portion outside the union, or it is not water and not chips. Same way, same statement. And that's 56. And that probability is 56 over 755. And lastly, that a learner buys water or chips. Now, water or chips is the union of the two events. So it's everything with the exception of this 56. So the easiest way is simply to subtract 56 from 755. Therefore 182 plus 304 plus 213 is the same as 755 minus 56, or 699. So the probability that a learner will buy water or chips is 699 over 755. We have come to the end of the video on probability. Remember, as I've mentioned earlier in many cases, to consult textbooks for additional examples. You need to attempt as many as possible other similar examples on your own. Compare your methods with those that were discussed in this particular video. Repeat this procedure until you are confident. And please do not forget, practice makes perfect. You only learn mathematics by understanding what you are doing. And then, if you understand it, please remember you still don't know it. Therefore, you must practice to perfection. Good luck and goodbye.